This is Vyshnavi. Welcome to Signals and System. Let us discuss about the analogy between vectors and signal, orthogonal signal space and complex orthogonal signal space. First thing, we have to discuss about the analogy between vectors and signals. Here we have to know about the vectors and signals. What is vector? A vector contains magnitude and direction. The name of vector is denoted by boldface type and their magnitude is denoted by lightface type. Let us consider one example. Here V is a vector with magnitude V and consider V1 and V2 are the two vectors as shown in the following diagram. Let the component of V1 along with the V2 is given by C1 to V2. The component of vector V1 along with the vector V2 can obtained by taking a perpendicular from the end of V1 to the vector end of V2. Let us see the figure. Here C1 to V2 be the perpendicular of both V1 and V2 vectors. The vector V1 can be expressed in terms of vector V2 V1 equal to C1 to V2 plus VE. Here VE is the error vector, but this is not only the way of expressing vector V1 in terms of V2. The alternate possibilities are V1 equal to C1 V2 plus VE1. Here VE1 is the error vector of 1. Here the next one is V2 equal to C2 V2 plus VE2. The error signal is minimum for large component value. If C12 equal to 0, then two signals are said to be orthogonal. Dot product of two vectors V1 dot V2 equal to V1 dot V2 cos theta. Here theta is the angle between the V1 and the V2 vectors. V1 dot V2 equal to V2 dot V1. The components of V1 and V2 equal to V1 cos theta equal to V1 dot V2 by V2. From the diagram, components of V1 and V2 equal to C1 to V2. Here C12 equal to V1 dot V2 by V2. Let us discuss about the signal. The concept of orthogonality can be applied to signals. Let us consider two signals f1t and f2 of t. Similar to vectors, you can approximate f1 in terms of f2t as f1t equal to c1 to f2t plus fet for T1 is less than T less than T2. FET equal to F1T minus C1 to F2T. One possible way of minimizing the error is integrating over the interval T1 to T2. From the integration 1 by T2 minus T1 integral T1 to T2 Fe of t dt. Here Fe of t equal to F1 of t minus C1 to F2 of t. and apply in the FE of t. However, these steps also does not reduce the error to appreciable extent. This can be corrected by taking the square of error function. Now we have to square the FE of t and apply the formula of FE of t, where epsilon is the mean square value of the error signal. The value of C12 which minimize the error you need to calculate. Let us do the derivation and integration of the derivative of terms which do not have C12 term or 0. And C12 equal to integral of T1 to T2 F1 of T F2 of T dt by integral T1 to T2 F2 square of T dt. The component is 0, then two signals are said to be orthogonal. Put C12 equal to 0 to get condition for orthogonality. Let us discuss about the orthogonal signal space. An orthogonal signal space uses a set of mutually orthogonal signals to represent any arbitrary signal in the space where the integration of the product of any two distinct signals is 0. Orthogonal signals as basic function. A set of orthogonal signals can be used as basis, similarly to how orthogonal vectors form a coordinate system in a vector space. Linear representation. An arbitrary signal can be represented as a sum of these orthogonal basis signals. Complete set of orthogonal signal. If set of orthogonal function is complete, then the linear approximation of signal can become an exact equality. Inner product. The condition for orthogonality is defined by an inner product, which is a definite integral over a specific time interval. Let us consider a set of n mutually orthogonal functions x1 of t, x2 of t and so on xn of t over the interval t1 to t2. As the functions are orthogonal to each other, any two signals xj of t, xk of t have to satisfy the orthogonality condition. That is, integral t1 to t2 x1 of t, xj of t, xk of t dt equal to 0, where j is not equal to k. Let t1 to t2 x square of t dt equal to kk. Let a function f, it can be approximated with this orthogonal signal space by adding the components along mutually orthogonal signals. Let us do the derivation. Mean square error. Epsilon equal to 1 by t2 minus t1 integral t1 to t2 f of t minus summation of r equal to 1 to n Cr xr of t whole square dt. The components which minimizes the mean square error can be found by d epsilon by dc1 equal to d epsilon by dc2 and so on, d epsilon by dck equal to 0. Here d by dck of t1 1 by t2 minus t1 integral t1 to t2 f of t minus summation of r equal to 1 to n Cr xr of t whole square dt equal to 0. All terms that do not contain ck is 0. In summation, r equal to k terms remain and all other terms are 0. Therefore, ck equal to integral t1 to t2 f of t xk of t dt by in integral t1 to t2 xk of x square of t dt. Let us consider one example. Show that the following signals are orthogonal over an interval 0 to 1. F of t equal to 1 and x of t equal to square root 3 1 into 1 minus 2t. We know that the orthogonal integral t1 to t2 x of t f of t dt equal to 0. Here limits are 0 to 1. Integral 0 to 1 f of t value is 1 and x of t is root 3 1 minus 2t dt. Root 3 dt minus, we have to separate the terms and integration we get the 0. Two signals are orthogonal over an interval 0, 1. Complex orthogonal signal space. Orthogonality in complex function means their inner product is 0, which is defined as the integral of one function multiplied by the complex conjugate of other over an given interval. If f1 and f2 are two complex functions, then f1 can be expressed in terms of f2 as f1 of t equal to c1 c2 f2 of t with negligible error, where c12 equal to integral t1 to t2 f1 of t f2 into of t dt by integral t1 to t2 f2 of t whole square dt, where f into 2 of t equal to complex conjugate of f2t. If f1 of t and f2 of t are orthogonal, then c12 equal to 0. Here the integral t1 to t2 f1 of t f2 into dt equal to 0. The above equation represents orthogonality condition in complex function. Let us take one example of complex exponential signals or orthogonal function. Given, let us consider two complex exponential signals x of t equal to e power jn omega naught t equal to and y of t equal to e power j m omega naught t, where m and n are integrals. Let the interval be t0 to t0 plus t, where x of t and y of t are orthogonal over the interval t0, t0 plus t. If t0 integral of t0 to t0 plus t, x of t into y of t dt equal to 0. Let us do the integration part of the orthogonal signal space. We have to get the 0 of, because orthogonal function becomes 0. Thank you for giving this great opportunity.